In this video we look at how side groups can affect the crystallinity of a polymer, particularly focusing on polypropene. So if we think of a polypropene monomer, we have 3 carbons in a row which have this many hydrogens on them. And the repeating unit is shown here, okay, with the methyl group circled. Okay, so there's your methyl group, and then the rest of it that repeats is here around the outside. So there's your carbon 1, there's your carbon 2, and there's your carbon 3, and here we've got 1, 2, and 3. So this repeating unit, you can see, can either have methyl groups on one side or another side, and that makes a difference as to how crystalline the substance ends up being. So the methyl group can be on either side in a random kind of order. We call this atactic, and this means that there's no particular order to it at all, and this is the least crystalline arrangement. If you have isotactic, that means that all of the methyl groups are on one side, and this one is somewhere in the middle. This is quite a crystalline structure, and that's because the chains are able to get closer together and pack in a more ordered fashion. Okay, so they can get closer together and they're closer packed. Okay, therefore more crystalline. Then we've actually discovered that we can actually alternate, but in a regular order, where the methyl group goes. And by doing this, we call it syndiotactic. By doing this, it actually allows it to pack even better. And so even higher levels of crystallinity can be achieved by doing that. But we are still looking into ways in which we can actually use these things. So the more crystalline, just as a recap, the more crystalline, the harder, more rigid the material, and therefore its uses would correlate with that.